Hello, this is Mr. Collier, and today we're looking at the complex plane and the modulus argument form of a complex number. So you're familiar with the regular real number line where we have 0 and 1, 2, root 2 is in here between, pi is over here somewhere. Okay, so the real numbers can be represented on a number line. Now when we introduce complex numbers, we can introduce an imaginary axis, and let's label this actually imaginary part of a real number or a complex number, and the real part of a complex number. So we can graph a complex number on the what we call the complex plane or the argon plane by using the x value as the real part and the y value as the imaginary part of a complex number. Okay, so here we have this complex number, p, and we have a is the real part, b is the imaginary part. So let's look at an example of how to graph some of these complex numbers. So if we have z1 is 3 plus 7i, then let me just relabel these. This is the real part, and this is the imaginary part of the complex number z. And so we have 3 and 7i, so 3 is the real part, 7 is the imaginary part, so we can graph it right here. So that is z1, and sometimes we like to draw a line over to the complex number. Okay, so it's in the first quadrant because both of those are positive. Now next we're going to do z2, and the real part is negative, so we're going to be over here. So negative 2 on the real axis, and 5 is the imaginary part, so z2 is going to be over here. Okay, oops, let me just fix that. Okay, so next we're going to do z1 plus z2. We can do it algebraically or graphically actually. So if we add z1 and z2, we add the real parts, and we get 3 plus negative 2, we get 1. And 7i plus 5i, we get 12i. Okay, so that's going to be the complex number 1 plus 12i. Let me do that in red. So 1 plus 12i is right here. Okay, now notice I can also treat these complex numbers like vectors. Okay, so this is the vector to z1, vector to z2. If I want to add these two vectors together, I can go from z1 and go the same direction. So this is left to up 5, so I can go left to up 5 from z1, and here I get z1 plus z2. Okay, so you can figure it out graphically or algebraically. Next, we're going to subtract them. So 3 minus negative 2 gives you 5. 7i minus 5i gives you 2i. Okay, so 5 plus 2i is over here. 5 plus 2i. And so notice if we wanted to subtract the complex number 2 from the complex number z1, we can go in the opposite direction of the vector z2 right here, right? So we can just go this way, okay, which is right to down 5 instead of left to up 5. Okay, so this is the complex number z1 minus z2. So you can see the relationship between complex numbers and vectors is adding complex numbers is like adding vectors. Okay, so you can think of them as one and the same. Next, actually we're going to skip right to this here. So we can think of a complex number as an x and y coordinate on the Cartesian plane, but also we can think of a complex number, and let me relabel this. The real part, this is the imaginary part. So we can also plot a complex number just based on the angle here, okay, which is called the argument, is the angle that the complex number makes with the x-axis or the real axis. And this distance right here, okay, this distance is called the modulus. Okay, that is the distance from the origin to the complex point P. Okay, so we can write modulus of z equals, okay, these bars, this looks like absolute value. And if you think about real numbers, the absolute value of a real number is the distance from the origin. And that's exactly what we have right here. The distance from the origin is what we call the modulus. So it's sort of like absolute value. And we can calculate the modulus by using Pythagorean theorem, right? So this distance here is root a squared plus b squared. Okay, and sometimes we use the letter r because you can think of it as maybe the radius of a circle or something like that, right? Okay, so r equals the modulus of the complex number. It is, okay, that's like, this means modulus of the complex number, and it's root a squared plus b squared. We can always give it the Pythagorean theorem. And of course, to get the angle, we can do arctan b over a. Okay, but be careful. Sometimes we have to figure out which quadrant the complex number is in order to figure that out. So I'm going to look over here right now. Given that this complex number, what is the relationship between the modulus of the conjugate and the modulus of the complex number? So now we know the modulus of the complex number is root a squared plus b squared. And if we look at the conjugate is going to be a minus bi. So the modulus of the conjugate is going to be root a squared plus negative b squared. And you can see they're exactly the same, right? Negative b squared gives you b squared. So the modulus of the conjugate and the modulus of the original complex number are the same. You can see that graphically as well, because the only difference between the complex number and its conjugate is the imaginary part becomes negative. So the graph of the conjugate is just a reflection in the y-axis. Okay, so the conjugate would be over here. Alright, and you can see from this that the r value, or the modulus, is going to be exactly the same. We've got the same triangles just flipped upside down. Okay, so that's something that's always true there. Let's go back up here now. So now we know what modulus is. We can answer these questions. So this is a set of all complex numbers such that, this line means such that, the modulus equals 3. So that means the distance from the origin is 3. Okay, and of course that means a circle with radius 3. Okay, that's the real axis and the imaginary axis here. Okay, now this one's a bit different. This is less than or equal to 3, so this complex number has a modulus less than or equal to 3. This one, this one, this one, this one. So we can shade in the entire circle. Okay, so 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So here it is, and you can shade it all in. And that's actually called, if you're interested in this is not important for complex numbers, but this is called a disk, and this is called a circle. The definition of a circle is a set of all points that is equal to the radius away from the center point. Anyway, a disk is when you fill it in. So that's technically a disk, and this is technically a circle. Going back to this section, so we call this angle the argument. Okay, so we call this angle the argument, the angle that it makes with the positive direction in the real axis, and of course the modulus is the distance from the origin. So this means, okay, let's say we have this angle here is pi over 4, okay, like 45 degrees, because it makes a 45-degree angle with the x-axis, or the real axis. Now if you got an angle over here, right, we would normally consider this to be negative pi over 4. Okay, it's the angle it makes with the real axis. So usually we think of complex numbers in the complex number plane as going from 0 to pi and negative pi to 0. Okay, but it's perfectly acceptable, especially on the answer key of IB exams, to write this angle as 7 pi over 4, right? If you go all the way around from here to here, okay, it's almost 2 pi, but it's 2 pi minus the pi fourths gives you 7 pi fourths. So you could call it 7 pi fourths, but most mathematicians prefer this one. Okay, one reason is because you can see that if you have conjugates, the argument are actually one is a negative of the other one, right? Okay. All right. So next, so you can see this down here. Normally we have this is the range of the argument, but most mathematicians prefer this one right here. Actually, it could be. I was going to say it could be equal to pi as well. So we need to change that to equal to pi. And the angle here, yeah, could be equal to 0. So you should change this to a less than or equal to sign here. Alright, so next we're going to look at a few things. So let's just draw a little complex number plane here again. So remember, A is the real part, B is the imaginary part, and we've got an angle in here, theta, the modulus, right? And R is, the angle theta is the argument, and R is the modulus. So you can see here from the diagram that A is actually R cosine theta, right? So cosine theta equals A divided by R. So A equals R cosine theta. And similarly, B equals R sine theta. Alright, so this is a way of helping you change from modulus argument form to Cartesian form. We'll see that in a second. So also note that we saw this before. R equals root A squared plus B squared, and the angle, the argument is equal to arctan B over A, right? B over A. Okay, but be careful of that one, because you have to check out the graph to see what quadrant the complex number is in. So you can see now we start off with a complex number, right? And in that complex number we can write like this. But we can replace the A and the B with R cosine theta and R sine theta. Okay, factor out the R. And because we're going to be writing this many times when we're doing complex numbers, we've come up with a shorthand notation called cis. Okay, so cis means cosine plus I sine theta. So it's just a short way of writing it. Okay, so this is modulus argument form, and sometimes called polar form or trig form. Okay, it's got a modulus and it's got an argument, so it's called modulus argument form. This one's called Cartesian form because it's just like plotting coordinates, Cartesian form. Okay, and we'll look at one more form a little bit later on actually. We're going to convert this number here into modulus argument form. So we can use what we have right here, or maybe over here. So the modulus equals root A squared plus B squared, so that's negative 2 root 3 squared plus negative 2 squared, which equals root, that's 4 times 3 is 12, plus 4, root 16, which equals 4. And the argument, arctan B over A, well that's negative 2 over negative 2 root 3, which is arctan 1 over root 3. So let's draw that. Actually, let's draw a little diagram of the complex number. So negative, so we're over in this quadrant. The real part is negative 2 root 3. The imaginary part is negative 2. Okay, you don't need to write the I. This is implied because it's on the imaginary axis. Okay, so our triangle looks like this. Okay, so this angle, this is this is going to be 2, and let me just redraw the triangle here. So this is like 2, and this is 2 root 3. This is pretty much the same as 1 and root 3 right here. So this is a 60-degree angle, which is pi thirds, and this angle here is pi 6. So this angle right here is pi 6. So that means this angle is negative 5 pi out of 6. Okay, so that is the argument, negative 5 pi out of 6. But it's also perfectly acceptable to go this way according to most IB mark schemes, and you could say theta equals 7 pi out of 6, right? Pi plus pi out of 6. Okay, so that's the argument, and that's the modulus. We can write z1 then as 4. I'll write this, 4 cosine negative 5 pi out of 6 plus I sine negative 5 pi out of 6. Or you can just write it as 4 cis negative 5 pi out of 6. Okay, so we just convert it from Cartesian form into modulus argument form. Next, let's take a look. This one is going backwards, and actually, if you look very carefully, you'll get the exact same thing, right? 7 pi out of 6, 7 pi out of 6. Let's just verify that. You can do 4 times cosine 7 pi out of 6 plus I sine 7 pi out of 6. Okay, 7 pi out of 6 is more than pi, it's over here. Alright, and let's do the, CAST. So cosine and sine are negative here, so we're going to get negative numbers for both of those. Plus I times, so we're going to get negative numbers for both of those. Let's draw the triangle for pi out of 6. Okay, some of you might have this memorized, but there it is, 1 root 3, 2. So cosine pi out of 6 is root 3 over 2, and sine is going to be 1 over root 3. 1 over 2, half. Okay, so let's go ahead and simplify this. And 4 times this will give me negative 2 root 3. And 4 times this will give me minus 2i, which is the original one we had, so you can see you get the same thing. Okay, so that's changing from modulus argument form to Cartesian form. Okay, next couple of useful things or identities involving modulus. So here, if you multiply a complex number by its conjugate, it's the same as squaring the modulus. So let's prove that one first. So if you have z times z star, the conjugate, let me just write this as multiplication like that. This equals a plus bi times a minus bi. And we saw before, multiplying the conjugate, you get things to cancel, and it's just a squared plus, well, you're going to have minus b squared I squared, but I squared is negative 1, so it's going to become plus b squared. Okay, so, but you can also write that as root a squared plus b squared all squared, right? Because the squaring the square root will cancel, which is equal to this. Okay, the magnitude, the modulus of the complex number is just root a squared plus b squared. So this is the modulus squared, and we're done. Okay. Second one takes a little bit more work to prove. Let's start with the left-hand side. Equals the modulus of z1, z2, and we got two different complex numbers, so let's call them a plus bi times c plus di, and distribute. We're going to get ac plus adi plus bci plus bdi squared. Remember, I squared gives me a -1. I will collect the real parts now. The real parts are ac minus bd, and the complex parts are ad plus bc. Okay, so let me separate this from the other proof. So that's the left-hand side of this equation right here. And hopefully we get the same thing with the right-hand side. The right-hand side equals modulus z1 times modulus z2. So I think I just forgot one thing over here on the left-hand side. I forgot about I'm getting the modulus. Okay, so that is going to be equal to square root of this squared, okay, plus AD plus BC squared. Okay, so again, let's go back to the right hand side. So here we're going to have root a squared plus b squared times root c squared plus d squared. Okay, so if you multiply those together, we're going to get root a squared plus b squared times c squared plus d squared. All right, now it's starting to look closer, but not quite the same yet. So let's distribute this. We're going to get root a squared c squared plus b squared c squared plus a squared d squared plus b squared d squared. Okay, sorry I messed that up there. And then over here, with this one right here, okay, this is going to be a squared c squared minus 2 a b c d plus b squared d squared. So I've got the square root, and this one here is going to be plus a squared d squared, and we're going to have plus 2, let me write down here, plus 2abcd, and then at the end we're going to have a plus b squared c squared. So these cancel, and we get exactly the same thing as the right hand side. Okay, so that is a fairly long proof, and we're going to see later that if we write the complex numbers in a different form, then these proofs are much, much easier. So perhaps we'll revisit this one later, and I'll show you what I'm talking about. Okay, so that just proves that these quantities are equal, and you can use these in some other proofs later. So they're two very useful things to know. Okay, next we're going to look at what happens when we multiply two complex numbers in modulus argument form. So if it's in Cartesian form, you've got to do this and use the distributive property and FOIL this out and all that. But we can also multiply them pretty easily if they're in modulus argument form, and we'll see what happens now in a second. So if I multiply these two quantities together, we'll get z1, z2 equals, we'll multiply the r's together, those are real numbers, just multiply them. And multiplying these two brackets together, we're going to get cosine theta 1, cosine theta 2, plus cosine theta 1 times I sine theta 2, and then plus I sine theta 1 cosine theta 2. And lastly, let me squeeze it in there, I times I is going to give you negative 1, so you're going to have minus sine theta 1 sine theta 2. Okay? And like we usually do, we're going to collect the real parts and the imaginary parts and have those separate. So you're going to have cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 plus I times, now all the complex parts are here, cosine theta 1 sine theta 2, and then plus sine theta 1 cosine theta 2. Okay, now if you look really closely at the formula booklet for IBHL, then this is a cosine identity. Okay, this is equal to cosine of the sum of these angles. So theta 1 plus theta 2. Okay, and then this here is equal to, again from the formula booklet, sine theta 1 plus theta 2. Okay, and you can summarize this too if you want to write it shorthand. This is cis theta 1 plus theta 2. So we see we can multiply the moduli, or the moduluses, or whatever it's called, and you get R1, R2, and for the arguments, you get a sum, right? Okay, so you can just add the angles together. And that makes it pretty easy, actually, to multiply some complex numbers when they're in trig form. Alright, so next we're actually going to put this result to use, because we can write these numbers in modulus argument form and then multiply using this rule that we just developed. Okay, so let's figure out what Z1 and Z2 are first of all. So here's Z1, real part 2, imaginary part negative 2 root 3. So it's over here. Alright, this is 2. This is 2 root 3. So again, we got the ratio of like 1 root 3, 2. So this is this angle here is going to be negative because it's in this quadrant here. So negative pi thirds, like a 60-degree angle, right? So that is the argument, and the modulus there is going to be root, I'll call this R1 for the modulus of the Z1, root a squared plus b squared, so 2 squared plus 2 root 3 squared, so this is similar to what we did before, I believe, and we're going to get a 4 here if you work that out. Okay, for Z2, both of those are negative, so we got negative root 3 and negative 1. Maybe I should draw that a little bit more to scale, and it's a bit easier to see what kind of triangles we're dealing with. Alright, so this situation, this is root 3 and this is 1, and this is going to be 2. So we can already see now that our 2 is going to be equal to 2. Okay, the modulus is going to be equal to 2, and that angle is going to be, so it's like a 30-degree angle, so it's pi over 6. However, we're looking at it from the positive real axis, so this angle is actually negative pi plus pi over 6 is going to be negative 5 pi over 6, right? Okay, so that's the, we'll call that theta 2. Okay, and this one's theta 1. Okay, now we can use a result from before, and we can say that z1, z2 equals, multiply the moduli, we get 8, and cis, add these together. So we're going to add these together. Maybe I'll do the adding over here somewhere. Negative pi over 3 plus negative 5 pi over 6 is equal to negative 2 pi over 6 plus negative 5 pi over 6, which equals negative 7 pi over 6, right? So negative 7 pi over 6 is like you go back, you go clockwise pi, and then another pi over 6. Okay, so we're actually at, if you look at this angle right here, 5 pi over 6. Okay, so this is equal to, this product is equal to 8 cis 5 pi over 6. Okay? Alright, so that's our complex number in trigonometric form or modulus argument form. Okay, next we're going to divide, and similarly we can come up with a rule if we just divide these two quantities here. So you're going to have R1 divided by R2 times, well, this divided by this divided by this. Okay, so when we're dividing complex numbers, we need the denominator to become real or not have a complex number in there. So we're going to multiply by the conjugate, which is this. We just change that to the imaginary part to negative. And it's much easier than you think. There's going to be a lot of things canceling or simplifying here in a second. Oh, sorry, that should be 2 and 2. Be careful with that. Okay, so we're going to get R1 over R2 times, alright, we're going to get cosine theta 1, cosine theta 2, and in the middle here we're going to get, I'll write the I first. I cosine theta 1 sine theta 2. And here we're going to get I sine theta 1 cosine theta 2. And lastly, remember I times I is negative. I don't have enough room again. So it's going to be negative sine theta 1 sine theta 2. Okay, that looks about right. Close the bracket. Oh, there's no bracket. Alright. Okay, next. Oh, sorry, the denominator. So the denominator, remember, if you multiply by the conjugate, the terms in the middle will cancel. We're just going to get cosine squared theta 2. And here I times I is I squared. So negative I squared is negative 1, so it's just positive. And it's going to be positive sine squared theta 2. And this is an identity, right? This is equal to 1. So our denominator is going to become 1, so we don't have to worry about that. And this, let's collect those real parts and imaginary parts again. So I'll put in bracket. So we have cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, and the imaginary part, cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. Okay, I just realized I made a slight mistake back here. I had to multiply by a negative right here. Okay, so that should have been, oops, sorry, that's a negative. That means, here, cosine, this should have been a negative. This should have been a negative here. Actually, let's just write it all in red. This should be a negative. This one's okay. This one should have been positive. Okay, so that means this one here is positive, and I believe this one here should have been negative. So I messed those up, and now we have slightly different identities than we had before. Now, because this is positive, we use that cosine identity. It gets you theta 1 minus theta 2. And for the sine here, we're going to get sine theta 1 minus theta 2. Okay, so this is equal to R1 over R2 cis theta 1 minus theta 2. Okay, so this reciprocal now, we can look at the reciprocal as, well, let's think about the number 1. Number 1 is a complex number. Okay, here's the complex plane, and here is 1. Alright, the modulus is 1, oops, for this number. The distance from the origin is 1. And the angle that it makes with the positive real axis is 0. Okay, so we can actually use a rule from before for the reciprocal. So in this case, we'd have the numerator here would be 1. So it's going to be 1 over R2 cis, and the angle is going to be 0. So if we put 0 here, we get negative theta 2. Okay, next we're going to put these numbers into trigonometric form. So let's look at Z1 first. So Z1 is right here, 1 in the real direction and 1 in the imaginary direction. So that's like a 45-degree angle. So the argument here is pi over 4. And this is like a 1 root 2 triangle. So the modulus is root 2. So Z1 equals root 2 cis pi over 4. Okay, next we'll look at the other number. We have negative 1, and root 3 is over here. Okay, so we have this triangle. We have a negative angle. That's a tiny angle on this root 3 triangle, so that's going to be a, let's go over here. Theta 2 is going to be negative pi over 6. And this is going to be 2, right? Root 3, 1, 2 in that special triangle, so it's going to be R2 equals 2. So Z2, the complex number Z2 equals 2 cis negative pi over 6. Okay, so we can use what we did before. This is going to be just 1 over the modulus from here. So that's going to be, let's do that green, 1 over 2 cis, and the angle is going to be, if we look back, the negative, right? So it's negative of that angle, so it's going to be just pi over 6. So next we're going to do Z1 divided by Z2, and remember we can just divide the moduli, so that's going to be root 2 over 2, and cis of, well, we can subtract these arguments. Okay, so pi over 4 minus pi over 6 is, let me work it out on the side. So pi over 4 minus pi over 6 is going to come down to 12, so 3 pi over 12 minus negative, so it's going to be plus 2 pi over 12, which equals 5 pi over 12. So this is going to be 5 pi 12ths. Okay? Now use your results from C to find the exact values of sine 5 pi over 12 and cosine 5 pi over 12. So that's pretty interesting. Up until now, we've only been getting exact values of like pi over 3, pi over 6, and things like that. But you can use complex numbers to do all kinds of other things like this. So here, notice we had, when we divided these quantities, we got cis 5 pi over 12, so it's going to have something to do with that. So we had Z1 over Z2 equals root 2 over 2 times, I'm going to write out the cis as cosine 5 pi over 12 plus I sine 5 pi over 12. Okay, alright, so what we're going to do, and this happens a lot with complex numbers, is if we can write it in this form and we can write it in a different form, we can equate the real parts and equate the imaginary parts. So that's how we're going to get these exact values. Okay, so there's another way to do z1 divided by z2, and that's in Cartesian form. And if we do that, we can get the exact values that we want. Okay, so remember the Cartesian form of the quotient of these two complex numbers would be 1 plus I over root 3 minus I. Okay, if you go back and look at our z1 and z2, this is what they are in Cartesian form. So we need to simplify this, and we can multiply by the conjugate. So root 3 plus I over root 3 plus I. And we're going to get on the top, on the numerator, root 3 plus I root 3 plus I squared, which is a minus 1, over root 3 squared is 3, and this is going to give you a negative I squared, which is going to be a plus 1. And let's collect the real parts. Root 3 minus 1 plus I times 1 plus root 3 all over 4. And let me rewrite this. Standard form, maybe it's called, or rewrite it like this, where we separate the real and the imaginary part, and we have this. Okay, so we have the real part and the imaginary part, and over here we have a real part and an imaginary part. So I'm going to, so by equating real parts, we get, don't forget about this root 2 over 2. Root 2 over 2 cosine 5 pi over 12 equals this real part over here, root 3 minus 1 over 4. Okay, we just simply need to solve this now. So I'll multiply both sides by 2, and we get, this is a 2, and then divide by root 2. So I'll get cosine 5 pi over 12 equals root 3 minus 1 over 2 root 2. And I guess according to the mark scheme on most IB exams, we can leave it like that, but if you want to, you can rationalize the denominator, and we'll get root 6 minus root 2 over 4, right? Root 2 is, yeah, 4. So that is the exact value of cosine 5 pi over 12. And we do the same thing for sine 5 pi over 12. So we could say, I haven't got this very organized. If you have more room on paper, you could do a better job of this, but we could say equating imaginary parts yields. So we'll get sine 5, or root 2 over 2 sine 5 pi over 12 equals 1 plus root 3 over 4. Okay, so similarly to before, we can multiply both sides by 2, and then we're going to get sine 5 pi over 12 equals 1 plus root 3 over 2 to root 2, because we're dividing both sides by root 2. And we can rationalize if we want by multiplying by root 2 over root 2. And we'll get this is equal to root 2 plus root 6 over 4. So very similar to that one. Okay, so sine, this is the exact value of sine 5 pi over 6.